Hello, this is Mrs. Hobbs, and I am going to be speaking about circular motion and get you guys caught up with circular motion. And we have lectured previously on how circular motion works, and right now what we're going to talk about is centripetal force, gravitation, and satellites. And then we'll also talk about how those work in the real world. So, first of all, there's a lab. We're not going to do the lab. But we want to talk about centripetal force. And centripetal force is really an adjective. It describes other kinds of forces. So, for example, if you have heard of the story of David and Goliath, David has a sling that he swings around his head, and it throws a stone, and it kills Goliath. Well, that sling has a tension force to it. And what a sling is it's just a piece of string with a square in the middle, and you put a rock or something hard in the square, and you swing it around over your head, and then you let go one of the strings, and when you let go one of the strings, the rock flies on its last path. So you have to have pretty good timing, but it was a pretty effective weapon during that time. Well, the force that the sling or the strings had is called tension force, but that tension force was moving in a circular direction, so it's called centripetal force. And a centripetal force is always perpendicular to an object's motion, towards the center of the circle. Centripetal force and direction. So we know what acceleration is. And acceleration is either a speed up, a slow down, or a change in direction. So with force, a speed up, you have it, a force is going the same direction as the velocity. It builds to the velocity, that's a speed up. If the force is going the opposite direction as the velocity, that is a slow down. The acceleration is countering the velocity. And then finally there's something called turning, which is changing velocity, because velocity is both a magnitude and direction. And that turning is also a change in force because it's a changing in direction. Okay? So whether a force makes an object accelerate by changing its speed or changing its direction or both depends on the direction of the force. So this is actually a lab that some of us will do, some of us won't be doing it. But imagine tying a ball to the end of a string and twirling in a circle over your head, like a lasso or a sling or something. The string exerts a centripetal force on the ball to move it in a circle. The direction of the centripetal force changes as the object moves around you. Another example of centripetal force would be a person making a sharp turn. In a curve, the centripetal force that makes the person turn is actually friction force. So basically an object in motion stays in motion, an object at rest stays at rest unless acted upon by unbalanced force. That's, I think, one of Newton's laws. And the way that we've said it before is an object keeps on keeping on unless something changes it. Well, with inertia and centripetal force, an object keeps wanting to go the way it was, and there's a force that has to pull it back in and change it around. So in this case, the velocity wants to keep going straight, but there's a force pulling it in to make it turn. Okay, so it pulls the ball to the side. Okay, and so it goes in a 90-degree angle, and it ends up turning around. So centripetal acceleration increases with speed and decreases as the radius gets larger. And the easiest way to think about this is think about a car turn. If you do a sharp turn, there's a small radius and you end up flying around the back seat. An easy turn, a larger radius, less flying. Okay, same thing with speed. Fast turn, flying. Slow turn, not so much. So this has been review, and we are going to be getting to the meat and potatoes of it, where we're talking about Newton's second law. And it's relating force, mass, and acceleration. The strength of the centripetal force needed to move an object in a circle depends on its mass, speed, and the radius of the circle. And centripetal force is directly proportional to the mass. A 2 kg object needs twice the force to have the same circular motion as a 1 kg object, because it's got twice the mass, so you need twice the force. In other words, heavier things are harder to turn. Okay? Again, heavier things are harder to turn. Okay, next, centripetal force is inversely proportional to the radius of the circle. The smaller the circle's radius, the greater the force. An object moving in a 1 meter circle needs twice the force as it does in a 2 meter circle at the same speed. So again, think about a wide turn versus a sharp turn, right? Sharp turn, there's more force to make the turn. Wide turn, you need less force to make the turn. That's why sharp turns you may end up hydroplaning because there's not enough friction force to keep you on the road, whereas wider turns are a little bit considered safer because you need less frictional force to stay on the road. So you may have heard of centrifugal force, and there are things called centrifuges that spin things around like blood and separates the blood levels. But there really is no such thing as centrifugal force. People have the idea like there's a ride called the gravitron where they're spinning around and it feels like there's a force pushing them back into that wall. Well, that's not really a force, it's just the sensation of a force. So what is happening? Okay, imagine, this is why riding in the back of the trucks is illegal, by the way. Imagine you got a heavy box in the back of the truck. The heavy box, or the truck wants to turn, so the truck turns, but the box is keeping on, so it wants to go in a straight line. Okay, so it goes and keeps on keeping on until it hits the side of the truck, where then the truck side can exert a force on it to make it turn. Okay, so while it seems like the box is being thrown to the right side of the truck, the truck is actually turning underneath the box. So it's all a perception kind of thing. You're not being thrown, it's just that the car is turning underneath you and you're not exactly moving with it. That's why seat belts are there, is to keep you going the speed of the car and not keep on keeping on through the windshield. So now we're going to talk about universal gravitation and universal gravitation and orbital motion. So Sir Isaac Newton first deduced that the force responsible for making objects fall on Earth is the same force that keeps the moon in orbit. Beforehand, nobody had put the two together. They thought they were separate forces, which is a pretty big leap of understanding, because on Earth things just fall straight down, while in the stars, moons, and planets things fall in a circular pattern. So this idea is known as the law of universal gravitation. Gravitational force exists between all objects that have mass, and the strength of gravitational force depends on the mass of the objects and the distance between them. So you can see, this is not to scale, but you can see a picture of the Earth and a picture of the moon, and the moon is falling towards the Earth. And the force of gravity between the Earth and the Sun keeps the Earth in orbit and keeps the moon and the Earth in orbit and all of our satellites in orbit, and that kind of thing. So you notice the gravitational force between you and the Earth because the planet's mass is huge. Gravitational force tends to be important only when one of the objects has an extremely large mass, such as a moon, star, planet. If you tell a person on the North Pole and on the South Pole to point down, they'll be both pointing opposite directions. Okay, so I want to kind of point out something here. Why, this is a better image, I guess. Yeah, let's go here. Why does the Earth fall towards the Sun and the Sun not fall towards the Earth? And this is the idea of an inverse relationship, right? The forces have to be equal. As you can see, the picture here, you've got two small masses, the force is equal. A larger mass, the forces are equal. Twice the mass, the forces are equal. So the Earth exerts an equal and opposite force as the Sun exerts on the Earth. So the masses are different, the forces are equal, so what has to be the change? And that is the acceleration. If you have a small mass, you have a large acceleration. And if you have a large mass, you have a small acceleration. So if you have a large acceleration like the Earth around the Sun, that means that the Earth is changing direction more than the Sun is, and that explains why the Earth rotates around the Sun and why the Sun doesn't rotate around the Earth. Okay, so you have the universal law of gravitation depends on the mass of the object, so the mass of the Earth, the mass on you, and then the radius or the distance between them. And there is also this G called the gravitational constant. Nobody really knows what it is or why it is. We just know that the math works because of that. Okay. So M1 is the Earth or the Sun. M2 is you or the Earth. And then the distance between them has a big impact. Okay. So which has a greater impact, the mass or the distance between them? And the answer is the distance between them. And the reason why is, as you can see, it is a inverse relationship, and it's also an exponential relationship. You've got that squared. So twice the distance equals 1/4 the force, because 1 over 2 squared is 1/4. So the further you get away from your gravitational body that you're orbiting around, the less and less force there is. And that means that there's less and less acceleration. So, for example, Neptune and what used to be known as Pluto have longer years because they are accelerating around the sun at a smaller pace, and so it takes longer for them to rotate around the sun. Also, a good example would be Halley's Comet as well. Universal law of gravitation. So you can see the distance between them has a big impact, and the force on the moon is equal to the strength force on the Earth. And there's some practice math that we're not going to do. And then we think of satellites as like yellow or silver things that are running around the Earth, but satellites are anything. They can be the moon, they can be space junks, they're just anything that falls around the Earth. And what is happening is they are falling across as far as they are falling down. So their velocity is always tangent, as you can see here, always tangent, or at a 90-degree angle from where their force is. And so the acceleration keeps changing their velocity inwards. So they're basically falling as fast across as they are down. And we looked it up, and some satellites are going 15,000 miles per hour. So they're falling across as they are falling down. And there are artificial satellites that orbit or revolve around the Earth, like the Hubble Space Telescope and a lot of our GPS satellites and a lot of our cellular satellites. And then orbital motion is an ellipse. It's not actually a circle, but this is technically ellipses because it's not a perfect circle. So it's really hard to see how they're ellipses, but ellipse is just an elongated circle. So we're talking about centripetal motion and circular motion, but it's actually elliptical motion. But the circles are so big, it's hard to tell that they're actually not circles. So it's actually a pretty okay thing. I would suggest watching this again and making sure you understand things. We talked about the universal law of gravitation and how distance is more impactful than the mass. We talked about centripetal acceleration and how the heavier the object is, the harder it is to turn. And we also talked about how greater the radius is, the easier it is to turn. And we also talked about in centripetal acceleration how it's an adjective that describes other kinds of forces like tension and friction.